All right, so today's lab is reflection and refraction. Before I get started, quiz 4 is now available. You have till Sunday midnight to finish it, just like many of the other quizzes. What else? I believe since the labs are starting to be a bit ahead of lecture, we're going to be taking a sort of break next week. It's not that there's no lab, it's just um, I'm going to be having like a tutoring session next week. So bring your questions, anything that you have, and we'll make it so uh, everyone can work on, whatever they need to during next week. Let's see. Yeah, I'll put more in an announcement later. Uh, yeah, so the semester's almost over. Only about 2 more labs left. So 2 more actual labs. So that's not counting next week. And it's just like the last final push to get as many points as you can. Let's go over today's lab, which is worth a lot. It's not necessarily difficult though. Let me go to the page. It's worth 80 points. And it's not difficult. There's just a lot of small little things to fill in. Going to the instructions, there's some background. I know lecture might not be there yet, so these background videos could help if you are struggling. And then there's also this intro bit right here. This is practically what I'm going to go over in my notes in a little bit. I'll explain all of this in a way in a little bit. Okay, so going down to the instructions, we're going to do part 1 in Pivot and just watch some videos, answer some questions. Let's go to Pivot. And we'll see that on this page, it's just, like we've been doing, screenshots, answering the questions step by step. When we get down to this video, we'll see that there's this laser that's taped to this bicycle rim. Let me play it. Actually, in the pre-lab, it was a little choppy. Let me go like real slow like this. So the laser up top, you can't really see it. So this person sprays some water or like some small particulate that makes the laser beam visible. And the light comes in, bounces off of a little mirror that's right here at the base, right in the center. So let's see, they spray something, and so we can see the path of the light. And I'll leave it kind of like right here. So what we can do with this video is use the tools that are provided and measure some angles. For this one, we're just measuring the reflection angle. So we have this protractor. You're going to place the center, so the bottom of this little T right here, on the center, or right where the light hits the center of the wheel. So right on the axle. So right there. And there's a little picture underneath to make sure you do it right. What you're going to do is take a couple measurements and figure out for your own. You can fill out this table down below. I think it says so. It says to do that in the instructions. Paste your table right here. Okay, so that's the first part, is the law of reflection. Let's go to the second part, which starts to go over the law of refraction. So refraction is when light moves through a material. We have this laser up top, and it's moving through air, and then it is, and this second material is plastic. So again, someone sprays some mist so you can see the two light beams. And same sort of tools. This protractor is real neat in that there's a 0 on the top and the bottom, so you always are measuring the correct angle. We're placing the center right where it strikes the surface. So right about there. You're going to take a couple measurements and fill out another table. All right, so with this, we should sort of figure out some things that are happening with the law of refraction. And this column right here, that is going to be, this table will automatically fill out this graph underneath. And what you can do on this graph is, I believe it says, you're going to plot sine of one angle versus sine of another angle. So you're going to already put those, already going to calculate those. And that's why it says you need to add 2 more columns. Let's go to that down here in the instructions before all right, so given, so it says right here, add columns to the data table. So adding columns, and it will help us to graph. On the y-axis, this, for your own notes, you could put the sine of the first angle down here. You could put sine of the second angle. That'll sort of help out. Once we sort of figure out what's going on with this, we can then go to the second part so we're sort of figuring out law of refraction on this part. And we're going to use what we learned in part 2, finding an unknown index of refraction. So we're going to vet this simulation right here. Once we get there, it might look like this. Just hit the play button and it'll be what we are used to. We're going to go to the intro. And in here, you're free to sort of, play with this however you want. This is showing us both reflection and refraction. We can move this laser beam around wherever we want. We'd also change, We'd also change, the index of refraction of the materials. I'll go over that in a bit if you haven't heard index of refraction before. So we can sort of change this, see what changes, and also make those same sort of measurements. What we're doing in this PhET simulation is finding an unknown index of refraction. So after you get used to this, you can go and click on mystery A if your student ID number is even, or choose mystery B if your student ID number is odd. So you're going to try to find the index of these 2 mystery materials. Let's go back to this. So you're going to leave the top one as air. Then you're going to choose the bottom down here. So as whichever your ID number tells you to. And you're going to take some measurements, figure out what it is. All right. Take some measurements. It would go into this table that would help you, just like how you did in this part above. Okay. I believe that is pretty much it. There's a little reference table down below for you to check and sort of see what you think it is. So it's kind of small, this original. Like blow it up for that. So you can see there's a lot of different known indices of refraction. You're going to see which one you think it is and find the standard deviation, not standard deviation. You're going to find the percent error. Here's the percent error formula and some questions. And there's no space for it, but you're going to remember to put your conclusion at the bottom, as well as having your introduction at the top. So there's no blank to fill in. You have to remember to do that. And I think at the bottom, there's this spare graph if you wanted to do it by hand. All right, are there any questions with the procedure or any of this breakdown? What I'm going to be checking is I just want to see like any sort of table that you have for part 1. So it could be for that first part, and you could ask me questions. I just want to see that some sort of work for that first part. Okay, let me get into the notes. All right, so reflection and refraction. This is probably the first time you're hearing of these, depending on your lecture. So let me start at the beginning. So light, you may have heard from, some source anywhere, that light can be expressed or seen as a wave or a particle. So light. For this lab, I don't want to introduce both right now. For this lab, we're going to be considering it as a particle. So imagine like a stream of photons. A particle of light is called a photon. So just imagine like a stream of them all moving at the speed of light, the fastest possible speed in the same direction. I guess I could say like photon. And imagine this stream of particles. And if we like zoom out until we're sort of like at our own human scale, this stream of individual particles would then just look like a straight line, completely solid, moving at that direction. And this is called a ray, a light ray. This is where we can introduce like geometrical optics. So it's very easy to, see how light's going to move if it's always just a straight line. I can, follow a straight line. I could calculate angles. It's very easy. This is the introduction to geometrical optics. So now that we have these rays of light, let's talk about the law of reflection. The law of reflection is very simple. It states that theta I, or actually, before I even get here, let me do the picture before I write this down. I never know where to put it. I'll put it right here. So this is a surface. Imagine this is a mirror. Something that's completely shiny, and reflective. Reflective in that light will bounce off of it. You can assume perfectly. So a light ray will come in at some angle. And it's always going to be moving in a straight line. This is a little, wavy just because of my hand. I'm trying to draw this straight line, and it's going to strike the mirror somewhere. Right there. That's point right there. That's where it strikes. We need to sort of have a way to always know how to measure an angle. How can we tell what angle this is coming in at? So we need to define something like this. We need to find the surface normal. Something like that. So this is a line. The normal to the surface. Like this. Make this a dotted line. So the normal to the surface, normal to surface. That's where we're always going to be making our measurements from. So it's this dotted line that's always perpendicular to the surface. I'm going to get rid of that. So this light ray comes in, and we can actually measure that angle right there. This is theta I for incident angle, or I'll say angle of incidence. That just means the beginning or the first angle or the starting angle. So that's where the light's coming from. And we're always measuring from the normal to the surface. The law of reflection, this is turning into a mess. Let me put this down here, and let me put the picture up here. Sorry if you're following along. I want these to look nice. The law of reflection says that the incident angle, the angle of incidence, theta sub I, is perfectly equal to the reflection angle, theta sub R. So the angle that the light comes in is exactly equal to, let me try to, so it's going to be like, nope, good enough. It's going to be exactly equal to, let me try to, so incident angles from the normal, the reflected angle, that one, is also measured from the normal. So this is, angle of reflection. And they are perfectly equal. Always. So that's the law of reflection. Very simple. Let's go over. In order to go over refraction now, I need to first talk about an object's index of refraction. Index of refraction. Okay, so what is an index of refraction? It's just a unitless number. It's written like this, so it's just a n, lowercase n, and it's something that's equal to it's describing how light will move through a material. So you think of how easy or how difficult light can move through something. So is it like air? How easy can light move through that? Versus water, there's a different index of refraction for water. It's a little bit more difficult for light to move through the atoms of water. So in the equation, we have n equals c. That's the speed of light. Speed of light in a vacuum. So in a vacuum, there's nothing, absolutely nothing. So light can move at its fastest possible speed. That's c. And it's c over v. So velocity, or I'll put over here, speed of light in that material. In material. Okay, so we have, say the material is, I don't know, like diamond or something that has a lot of atoms in the way. Light has to sort of maneuver through. It's interacting with a lot of material. So the speed is going to be smaller. It's going to slow down a bit. So commonly we'll see that, for a lot of materials, this c on top, that's going to remain the same. But we're going to see that the velocity is going to be a smaller value. So since the speed of light slows down a bit and the denominator gets smaller, we should expect that the index of refraction will always be greater than 1. Right? So imagine if our material was, we wanted to know the index of refraction of a vacuum. So that's just speed of light, like this. So that's the speed of light in the vacuum over speed of light of the material, which is just the vacuum. And that is exactly 1. So it's never going to be less than 1. And for many of our experiments on Earth, we can assume, like this, index of refraction of air is very, very close to 1. So we can just say it's 1. That's made a lot of people's experiments easier to do. When in reality, it's like 1.0003 something. Since it's so close, we can just say it's 1. Okay, so we're able to describe how light can kind of slow down, and we can sort of label things, how easy can light move through them. Now we can talk about the law of refraction. Put it up here. Okay, so how do I want to, let me make this smaller. I need some room. So the law of refraction, also known as Snell's law. Let me put over here Snell's law. I'm going to do like a little simple explanation is how does light bend or how does light move when entering a material? That's answered by Snell's law. Let me give a little example that a lot of people use because it is, easy to think about. I'm going to put this example over here. So say we have a lifeguard at the beach. This lifeguard is walking on the beach and they're walking along the shore. And here's the, water line. Make that better. And they see that someone needs help out in the water. That person's right here. They need help. This is water over here. So that lifeguard wants to save this person. They need to get there as quick as possible. How should they move to get there? So they're currently in air. They're walking on the sand. They're in air. And there's the shore. This over here is water. So what's the shortest distance between the two? Shortest distance, just a straight line like that. But if you look at this straight line, think of how much of this straight line is in air. So only this small bit is in air. This much larger bit is in water. And I don't know about you guys, but I find it easier. I can move quicker through air. I could probably run faster than I swim. In fact, I know I do. So, I would get there sooner if I ran more and I swam less. Going like this all the way over and then straight down, that might be good too, but I'm sort of wasting time, not sort of making it at an angle. So what the lifeguard needs to do is judge the right angle to get there the quickest. The angle to get there would be something like this. Let me do it one more time. So something like this. That, and then like that. So a lot of the time is spent running, which they can do very quickly. And then just a small little bit is them swimming. This is the path of least time. Path of least time. So that's the fastest possible time to get there. So light also obeys the path of least time. Let me do my sort of just optics example now. So we have this light beam that's going to come in some random angle. That and strike the surface. Again, we need to know, which angle it's coming in at. So we need to know, or we need to have, the normal to the surface. That's this dotted line. So that will give us this incident angle. But we're not talking about something that's reflecting. This thing will be moving into the material. So I need to measure angles down here too. So I need to extend that same normal line down into the material. So light ray will come in and will be bent inwards towards the normal, the surface. And that angle right here, this one down here, I'll call theta T for transmitted. So now let me get to Snell's law. I write the formula out finally. It is the index of refraction of the first material times sine of the first, angle is equal to N2 sine theta 2. Now, instead of having 1 and 2, I could rewrite this formula as sine theta incident angle sine theta transmitted, like that. And what are the indices of refraction? So that's just the first material. So that's this up here. I don't know, we'll say N1, we'll say that's like air, sort of to match this example on the right. I'll say this N2 is water. So that's just the thing to always remember, is that light does this because it travels the path of least time. Okay, so we have a good start to the lab. Are there any questions with this material or the notes? Let me go like, let me go like that. Okay. Okay, let me get the breakout rooms ready. So I only, I just want to see any type of work you have for that first part. And then I'd say you're good. Like that. And don't forget, there is a quiz that's available. And next week will be a tutoring session. So bring your questions if you have any. All right, the rooms are open.